Eclipses are one of the coolest natural events out there. From an initial viewpoint, eclipses seem relatively simple. Oh, small space rock moves in front of big glowing ball of plasma, and then big shadow appears. And while this is technically true, so today, while we're in the middle of an international pandemic and not allowed to go outside, I'm going to attempt to explain how eclipses work, and hopefully not get anything wrong in the process. Lunar eclipses are, in my opinion, the more tame side of the eclipse coin. They follow the same basic rules as a solar eclipse would, but are easier to explain, so that's what we're starting with. So, the Earth and Moon all have these orbits around other planetary objects, with the Earth orbiting the Sun and the Moon orbiting the Earth. These orbits are not perfectly circular, because nothing's that easy, so they form something closer to an ellipse than a circle. Not only that, but not all of the orbits are on the same exact plane either. So, instead of being parallel to the Earth's orbit around the Sun, the Moon's orbit around the Earth is at a slight angle of 5 degrees in relation to the plane of the Earth. This slight angle is what determines if an eclipse will happen or not, both lunar and solar. So, back to lunar eclipses. When the sun shines its light on the Earth, it creates a shadow, as most things do when hit with light. This shadow is pretty long enough to be able to cover the Moon, despite the 238,900 miles that separate the Earth and Moon. Every so often, an average of 2 times every calendar year, the Moon's orbit will align with that of the Earth, allowing the Moon, in its full phase, to pass through the Earth's shadow. As this happens, one might expect that the Moon would darken completely, or at least to a somewhat decent extent. This assumption, however, would be wrong. Very incorrect. While the Earth does make a shadow, a little bit of light can go through its atmosphere. This light is filtered out to be red when it comes out, for the same reason a sunrise and sunset appears to be red, and it reflects off of the Moon. This makes the Moon have a startling red color. Pretty neat. Solar eclipses follow the same aforementioned rules that lunar eclipses follow. They can only occur when the orbits of the Earth and Moon become parallel with each other. Solar eclipses are like lunar eclipses, but backwards, almost. Instead of the Earth making a shadow to cover the Moon will go between the Earth and the Sun, creating a little tiny shadow on the surface of the Earth. From outside of the range of the shadow, the Sun looks completely normal in the sky. However, if one were to be inside of that shadow during the solar eclipse, they would see an amazing sight, which my doodles can do no justice. This is a solar eclipse during totality, the point at which the Moon is able to completely cover the Sun. Do you see that little white ring? That is known as the Bailey's beads effect. During the moment of totality, the faint corona, the aura of plasma that surrounds the Sun, which you cannot normally see, becomes visible, leaving a diamond-like ring where the Sun once was. And although this is super cool, I've been purposefully leaving out the less cool events. Partial and annular eclipses. Things are going to get a little bit more complex. Do you remember the shadows I've been talking about? Yeah, those are more complicated than I initially made them out to be. We'll start with the moon shadow on the Earth during a solar eclipse. The moon shadow is split into 2 parts, the umbra and the penumbra. The umbra is the center shadow. If you are in this shadow, you will see a total solar eclipse. The penumbra is the outside shadow, which surrounds the umbra like a donut, sort of. If you are in the penumbra during a solar eclipse, you will not see a total solar eclipse from where you are. You will still be able to see the moon make a big dent in the sun, but you won't get the full experience. This is known as a partial solar eclipse. Depending on the conditions, these shadows projected onto the Earth can be massive or pretty much non-existent. Not only that, but because of the ellipse shape that the moon's orbit forms around the Earth, there will be parts in the moon's orbit where it will be too far away from the Earth to have a total solar eclipse occur anywhere. You see, the sun and the moon have a special relationship in relation to the Earth. The sun is about 400 times bigger than the moon, but is also about 400 times farther away from the Earth than the moon is. This is why the moon and sun look the exact same size in the sky, and why total solar eclipses can even occur in the first place. So if the moon gets even a little bit too close to the sun in its orbit, you won't see a total solar eclipse. You will be viewing an annular eclipse. Make sure to know the difference between an annular eclipse and a partial eclipse. Lunar eclipses are less complicated with its relationship with shadows. The Earth, similar to the moon, will create an umbral shadow and a penumbral shadow. During a lunar eclipse, the penumbra matters much less than the umbra. As the moon slowly begins to enter the umbra, it'll darken to a significant extent. However, once it is completely within the umbra, it'll start to glow the red color that lunar eclipses are known for. While watching this, some of you may have thought that, so if the moon's orbit and the Earth's orbit become parallel twice every year, does that mean that solar eclipses and lunar eclipses should happen in succession with each other during their respective moon phases? The answer to that question is a yes. It only really makes sense. During the eclipse season, where the orbits are parallel/aligned, the moon will be able to cycle through a full moon to a new moon. If you didn't already guess, a lunar eclipse is only able to happen during a full moon, as it is directly behind the Earth in relation to the sun, and a solar eclipse is only able to occur during a new moon, as it is between the Earth and the sun at this time. Pretty neat.